Hello, my name is Aleksandra Milic and I'm a technical and R&D engineer at TEON. TEON is an Italian company that produces heat pumps and our production is based in Turin. I'm originally from Montenegro and I finished my bachelor studies at the University of Belgrade. I finished electrical engineering and then I finished my master's degree at Politecnico di Torino in renewable energy systems. Today I'm going to speak a little bit about the specifications of the design of our heat pumps, and I'm going to start by explaining the thermodynamic cycle of one of our most characteristic models. So if we have a graph that is pressure and enthalpy, and we have a saturation line of the refrigerant, what are we doing with the heat pump? We have a source that makes our refrigeration evaporate. The evaporation happens at a constant pressure. So in this graph, the evaporation is represented with a constant pressure line. So here we have an evaporator that is exchanging energy with a source. The source can be water or air or glycol water. Then we have a compressor that is increasing the pressure of the refrigerant, and at the same time it decreases the temperature. Then after the compression stage we have the condensation. Condensation happens in a condensator that exchanges the energy with our plant. Here it can be water, also air or different things. We are usually making water-water heat pumps, so both source and the plant side the fluids are water. And at the end we have a valve that is regulating the pressure drop between the condensation and the evaporation. One thing that is really characteristic for our machines is that we recover internally the energy from the thermodynamic cycle, because we have another heat exchanger here in this process. So after the condensation, that exchanges temperature with the gas before it enters the compressor. So we are using the high temperature energy and we are recovering it to preheat the gas before the compression. This is why our heat pumps work really well and are really efficient at high temperatures, because the higher the temperature we have of the condensation, we can recover more energy and we can increase our efficiency by 20 to 30%. One of our most characteristic designs is a double-stage machine that uses this heat exchanger here as both condenser and evaporator. For the bottom cycle, this heat exchanger acts like a condenser, and for the top cycle, it acts like evaporator. So we have the same thermodynamic cycle on the top, and we have two stages. This kind of machines are very useful for air-water systems when we are taking air as source at lower temperatures and we have to increase the temperature of the water up to 80-90 degrees. In this way we are increasing our efficiency, especially because we are using R600A, which is isobutane, in our top cycle, and we are using propane or R290 in our bottom cycle. Propane is known to be very efficient when the source is at really low temperatures. Isobutane is really efficient when it's working with higher temperatures, but it cannot work with low temperatures of air. So in this way we have a double cycle machine that uses air as a source and produces water up to 90 degrees, even if outside temperature is at minus 15 degrees. Now let's go see the machine. So let's see how the thermodynamic cycle that I previously explained looks like in reality. These two tubes are the tubes for the source. So this machine is modeled for is a brine water machine. So the source is glycol water. In reality, we dimensioned this machine to work with air source. So in this circuit, which is glycol water circuit, we add the dry cooler that exchanges energy with air. The glycol water enters here it goes to evaporator. This is the first evaporator, and it exits here and exchanges energy with the evaporator. After the evaporator, we have the compressor, that is this one for the bottom cycle. So the gas exits the evaporator, enters the compressor, and increases its pressure. Then, after the compressor, we have condense evaporator, where gas from the bottom cycle exchanging energy from the gas of the top cycle. After the condense evaporator, we have a valve, which is this one here. We are using electric valves. So this is the whole bottom cycle. What we have in the top cycle, we are starting from the condense evaporator, which serves as an evaporator in the top cycle. We are entering the second compressor. From that side, the gas it increases its pressure and exits here, and it goes to the condenser. This condenser exchanges energy between the gas from the top cycle and these two tubes that serve for water for the plant. After the condenser, we have a second electric valve that is controlling the pressure from the top cycle. And after the valve, we are entering once again in the condense evaporator. Here we have some acoustic insulation because compressors make noise, so to reduce the noise we are using these panels. Here we have different kind of sensors that are measuring pressure and temperature after the evaporator and before the condenser. We put them here so it's much easier to do maintenance when it's needed. Now let's go see the distribution board. We have this one open here. Since I'm an electric engineer, this is mostly what I'm doing here. I'm designing the electrical wiring schemes, the automation of the machine that is done with this PLC, and the connection port that is exchanging data. We are monitoring 83 parameters all the time in our machines. This is the PLC that is controlling the whole machine, and these are EVDs that are controlling the electric valves and the pressure difference in both cycles. These are the circuit breakers and the transformer. This part here is the protection of the motors. We have the general circuit breaker, the overcurrent protection, and we have the contactors with which we are turning on and turning off the compressors. We also have this module here that is measuring the total electrical energy that is being consumed. Now I'm going to explain some of the softwares that we are using for the programmation of the machine. For example, the first software that we are using is the control programmation of the PLC. First we have inputs. We are measuring 4 water temperatures, inlet and outlet of the source and inlet and outlet of the plant. We are measuring also temperature and pressures of the gas after the evaporator and before the condenser. We are measuring the flow rates and we are measuring other temperatures like outside temperature or indoor temperature of the place that is being heated up. Then we have one page for all the alarms that are antifreeze control and for example for the protection of the compressor, because if something doesn't work well, the compressor just shuts down to protect itself. Then we have a page for the regulation, which is PID regulation based on the inlet and outlet water temperatures and the set point of the machine. And then we have the outputs that are turning on and off the auxiliary elements of the system. For example, the circulator for the source, the circulator for the plant. The other software that we are using is the communication software with which we are controlling our gateway that is transmitting data to our server, where we are monitoring the behavior of all the machines, and is sending also data to our online platform where we can analyze the performance of the machines. Here we are defining all the variables that we are measuring and that we want to transmit, and also we are calculating some of the variables like efficiencies like COP and EER, and other parameters that need to be calculated and transmitted to the platform. I've been in HVAC industry for about a year now, and the thing that I like the most is being able to see all of our ideas and all of our designs come to life, being able to adapt to the challenges of the market, following the needs of the market, always developing new solutions, and always trying to push forward and to make something that hasn't been done before.